All right, welcome to the live. I am today going to go over some problems from probability section in prep for our test next week. So I've got to do a quick mic check. Give me 1 second. You can probably hear my phone in the background as it plays the intro that just came through. There's a little bit of a delay. I just want to make sure it looks like my mic's showing up okay. And it is. There it is. All right. So we're going to do a few problems. Got a few introductory things to go over. Introductory in the sense of we've been over them already, but let's just review them. But before we get to that, I want to take a look at a screen. I messed up my screens the other day accidentally, size-wise and consistency. So let me go back to that because I want to get your opinion on something because I'm kind of torn on this one. I think I talked about it a little bit in the last one. Let me go to what is now called workspace, but it's not workspace, it's this mess right here. So I've got this calculator up here right now, and since I have messed this up, let me go ahead and close that out, make this bigger. And I really need to advance that on the screen. There we go. The only problem is it cuts off a piece at the top. I'll work on that later. Anyway, as you can see here, I've got a calculator that has the same functions as our TI. I bought it for about $4.50. When you go into, say, second list, it looks like this instead of looking exactly like your TA. It's the same functions. It adds a little bit to it by telling you exactly what it does. Returns a minimum element of a list, and it shows you the syntax for it. I like this one. I've used it for a while, even on streaming on here, but I've got this other one. I like this one. The only thing I don't like about this one is that, let's say I go 98 times 63, enter. Enter. Well, this was cut off at the top too, so let me do something else. 85 times 69, enter. Enter. It's fine, but I need a darker screen there, and I need that to be bigger, so if I can figure out how to do that. So anyway, I'm torn between these two. So what I pose to anybody that's watching tonight, or anybody that watches the video on demand, especially for my class, help me out. Which of these do you like better? Do you like the newer format, which is just like a TI-84, slight difference in placement only because they use some different geometric figures, or this one that looks much more like it and you can see the numbers better? But when you go into, say, stat, it looks like this, which is the same but just slightly different. So anyway, let me know if you would. I'm going to leave this green one up for now, but we're not going to be working with this. Let me get back to what we're going to do tonight. So I'll stay with my, see how my circle shifted up and stuff. I got a few things off. Okay. As always, at the start of the stream, I talk about my stream because I'm such a professional. My camera that I'm using is a 4K AnchorWorks camera. I have an older 2015 Mac that I stream through, and I use Ecamm, which is kind of like OBS, except it's more drag and drop. It works better for me. The OBS was a mess when it came to sound and video for me. Too much finagling. I could not get it to, when I got it looking right on my screen, it never, my fans would start kicking in, and it just never, it was always an overload on my system. So anyway, that's what I do. I stream through there. I used to open up Doceri on here and stream using Doceri from my iPad to the screen, but that too was a drain on the system. So I backed off of that, and I have a program called Mirroring 360, which is a very cost-efficient program. It's only like $11 for a perpetual license. And so now I can stream 2 iPads, one with my calculator, so iPad mini that I've had for a while. I actually bought it refurbished from Walmart, and it was actually very good. It's like brand new. And then this one my wife got me years back, just a larger 10.2 inch that I use for the presentation, and I use the bigger one so I can write on. I probably need a Pro. That's too much money for what money I have. So here we go. So I'm going to stream now and talk about our chapter 3 review, test 2. That's next Wednesday. All right. So I got to get my wits about me because I'm used to using Doceri and having it up. So now I've got it flat. So I have to think a little bit about it. So let's talk about basic probability. Couple of refreshers, and we talked about these last night in class when I went over stuff. So you've got, I did not go to the fundamental counting principle last night, but we talked about range of probabilities rule. I talked about this right here. All probabilities are going to fall between 0 and 1 inclusive. We talked about that in detail. Talked about the law of large numbers last night and had a very good answer. Very good answer from a student in class. It went great. As an experiment is repeated over and over, the empirical probability of an event approaches the theoretical actual probability of that event. We talked about those two. Fundamental counting principle. If you've got one event that can occur in this many ways, let's say m ways, and you've got another event that can occur in n ways, then the number of ways the two events can occur in sequence is m times n. You can think about the fundamental counting principle, in my opinion, in terms of the tree diagrams, which I spent quite a bit of time on. If I'm flipping a coin, I get heads, tails. Heads, tails, and so on. So the sample space from this is going to look like heads, 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 tails, and so on. In other words, we're going from here to here consecutive events, and from here to here consecutive events for that sample space. So, just a little reminder on some of that stuff. Complements, our old handy dandy Venn diagram. If you are looking at, in this example, looks like we're rolling a die, and you're looking for what's the probability of rolling a 5 or a 6. That event 5 or 6 is in that one circle. Everything else is the complement of that. That's if you roll anything but 5 or 6. It's binomial in that sense, where 5 and 6 are getting a 5 or a 6 is your success. Anything else is a failure. So, let's move right into the meat of it. I know the folks coming from my class certainly want to know, what's the test going to look like? Well, I don't have the test here, but I have pieces and parts. So let's talk about this. Types of problems you might see, and these are basic probability problems in this statistical analysis class. You toss a coin and randomly select a number from 0 to 9. What is the probability of getting tails and selecting a 3? Okay? If you remember, there's a key word here with the and. So you toss a coin and randomly select a number from 0 to 9. What is the probability of getting a tails and selecting a 3? Well, without going into the multiplication rule, which is really what it breaks down to be, we could just look at, see what's the best color to use here. Not sure. We could just look at the fact that I'm going to toss a coin. The outcomes from the coin can either be heads or tails, right? So in other words, the first thing we're going to do is toss the coin, right? The second thing we're going to do, and I'll probably have to go darker for this second, so maybe I'll stick with blue. Second thing we're going to do is randomly select a number from 0 to 9. Okay, this is going to get messy, but it looks like this. If I toss the coin and get heads, after heads, I could get uh, 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8. This is terrible. 9. That's okay. So in other words, off of that tail, I can get one of those other outcomes that come from, what was it? Selecting a number. Randomly selecting a number. If I go out from tails, it's going to be the same thing. So I'm going to get 0, 1, 2, 3, 4, 5, 6, 7, ... I'm going to put, wow, that's terrible. So, but this is our tree diagram, right? So our sample space would look like this. I think green may work if I do it here. My sample space is going to look like heads, 0. Hey, Tiante, thanks for stopping by, man. Appreciate it. I've got heads 0, heads 1, heads 2, heads 3, heads 4, heads 5, ... all the way through heads. And then in this same sample space, in this bracket, I'm going to have tails 0, tails 1, tails 2, ... all the way to tails 9. Right? Very much a sketch here. I'm more walking through it verbally than I am on paper, because I ran out of room because of the choice, the problem that I chose. So we're looking at what is the probability of getting tails and selecting a 3. Okay. So we're looking at the probability of tails 3. Well, that only happens one time. It happens right here when you get a tails and when you get a 3. Well, the probability of getting tails in the flip of a coin is 0.5. And the probability of getting a 3 in that set of numbers, well, I don't know how many numbers are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 because we include the 0. So 1 out of 10. So when you look at the probability of getting tails, and then the probability of getting a 3 is 1 out of 10. So you've really just got a 1 in 20 chance of getting that. And remember, in my class, break it down to the decimals and round it out to whatever decimal places that I ask you to on the assessment. And in this case, we just get 0.05. And I covered it up with my big head down there at the bottom. I was trying not to reach that bottom. That's why I went to the circle down there. But it's okay. So hopefully this makes sense. I talked through it. So your answer for the probability of getting a tails on the flip and a 3 when you randomly select a number is going to be 1 out of 20, which is 0.05. Okay, so there's one example of one of the types of problems that you might be able to see, and a little review of a tree diagram, albeit a very poorly drawn one, but you get the idea. Which, if you remember right back during class, I said that's, to me, is the big thing with tree diagrams, why they're so powerful, because you can get an idea of where things are going and feel it out real quick because you've got a visual representation of the experiment going on. Sample space, very crudely drawn out by me, but just to get it started so I know where I'm at. And then I went back to the problem. I'm trying to find the probability of getting tails and selecting a 3. And the answer here will be 0.05. All right. Let's look at a different example. 5 of the 100 digital video recorders, DVRs, in an inventory are known to be defective. So 5 of the 100. Okay. What is the probability you randomly select an item that is not defective? I'm looking at this. I'm going to expand this problem out, actually. 5 of the 100 digital video recorders in the inventory are known to be defective. Probability you randomly select an item that is not defective. Okay. So, five out of 100 500s. That's very easy. It's 0.05. 500s represents defective. So what represents not defective? So these are the defective ones. Therefore, not defective would be the rest of it, which would be 0.95. Add that up, you get 1. So if you're looking for the probability that you randomly select an item that is not defective, it's 0.95. You reach in there, and in this case, there's 95 out of 100 of them that are not defective. So you got a real good chance at grabbing the not defective one. So the probability randomly selecting an item that is not defective is just 0.95. This, when you go back to what we talked about in class, quite in detail actually, with the algebraic manipulations of the complements, where you're looking at e plus e prime equals 1, and then you could have e prime equals 1 minus e, or e equals 1 minus e prime. If you remember that, that's what I just worked with. I just didn't write all that out, but I had to recognize that 5% of these were defective, leaving 95% that were not defective. So in essence, really, this is a very simple problem. This is one of those problems that I call gimme problems. In other words, give me more of these, because this is not too bad in the big scheme of things. All right. Okay, let's talk about a security system. And now we're talking about, if you go back, so I can go back, yeah. The fundamental counting principle. And we're talking about, in this security system, if you remember, Yeah, easiest way to look at this. An access code consists of a letter followed by 4 digits. So an access code consists of a letter followed by 4 digits. Typically how I approach this, I just sketch on a scratch sheet of paper. I'm like 1, and then 1, 2, 3, 4. So my code looks like that. That's the there's something in the first block, second, third, fourth, and fifth, right? So letter followed by 4 digits. Well, how many letters are there? So I have 26 possible letters I could put there. So what we're looking for here, find the number of possible access codes. I'm sorry, I didn't even read through what we were looking for. Find the number of possible access codes. So in that first block, there's 26 letters possible that we could have there. In the second block, and we have some constraints here, but we're followed by 4 digits. Well, we can only have 0 through 9. That's 10 possibilities, but it says here, any letter can be used, so my 26 is right. But the first digit cannot be 0, so there's 9 choices for that first block, and the 9 choices would be, I can't do 0, so that's out. So it's just 1, 2, 3, 4, 6, 7, 8, 9. So I got 9 choices. But now in this second block, I'm wide open. I can choose a number and I can include that 0. So now I've got 10 choices for that block, 10 for that block. And then the last block, it says the last digit must be even. All right. Given that 0 is now in the set, keep it at least the same color, and that 0 in a lot of the text is considered to be an even number, we're going to roll this way. So we've got even numbers right here. We've got 1, 2, 3, 4, 5. So I've got 5 selections for this last one, and that's it. Now, I'm going to multiply these to find out how many possibilities we've got for access codes. So I've just got 26 times 9 times 10, 10 times 5. 117,000. So your answer to this problem is 117,000. And before I move on, I want to make sure that what I've got here for an answer that I met my constraints. So an access code consists of a letter followed by 4 digits. Okay, no problem there. Any letter can be used, so 26 for that is right. The first digit cannot be 0. So I've got 9 digits left, so that's right. And the last digit must be even, 2 10s and then a 5. Okay. And that last is including, see, 0, 2, 3, 4. Yeah, is including 0 as an even number, which a lot of text will tell you is an even number. So we'll roll with that. We got 117,000. What is the probability of randomly selecting the correct access code on the first try? This is just an extension of what we have here. And again, I wish there was on Keynote, which is an Apple presentation product, which is what I'm using here. I wish I could erase this off. So I'm going to have to go kind of askew up in the corner here away from it. But we're going to talk about this next. What is the probability of randomly selecting the correct access code on the first try? Well, I'm going to switch colors so we can differentiate. And I've got that first digit and then 4 following it. Okay. Well, what is the probability of selecting the correct letter in that first block? Well, it's 1. There's 1 letter that's correct out of 26. So the probability of selecting the first slot with those letters correctly is 1 out of 26. The probability of selecting the correct number in that first one where 0 can't be in there is 1 out of 9. 1 out of 10. 1 out of 10, is that showing up okay? Yeah. And 1 out of 5. 26 times 9 times 10 times 10 times 5 is 117,000. And 1's across the top multiplied together just to be 1. And so your answer to B, what is the probability of randomly selecting the correct access code on the first try, is 1 over 117,000. Not a very good probability if you're a burglar. Okay, and then what is the last question here? C says, what is the probability of not selecting the correct access code on the first try. Well, if the probability of selecting the correct access code on the first try is 1 out of 117,000, then this other, still 117, this is C, still 117,000 in the denominator, but instead of 1 out of that, you've got 116,999. Yep. So there it is. That is the answer to C, the probability of not selecting the correct access code on the first try. Okay. Not too bad on this. So the first thing we did was find the total number of possible access codes. We found that to be 117,000. We followed the constraints. I even went back and double checked, pretended I was taking the test to make sure I didn't miss something. What is the probability of randomly selecting the correct access code on the first try? I got that in green right here. 1/26th. Probability of getting that one letter correct if you're choosing it randomly. 1/9, getting the one digit correct if you're choosing it randomly. And so on, gives you 1/117,000. And then the last, we're just looking for the complement. What is the probability of not selecting the correct access code on the first try? And that is 116,999 over 117,000. Because, let me see if I can fit it in here. Because if this is E, and this is E prime, this is the complement of this other one, we know that E plus E prime is equal to 1. And that's what I'm using here to find that 116,999. All right. Okay. No questions? A couple of folks in. I know Tiante stopped by to say hello. I don't know if he's still in. Doesn't look like anybody's in here right now. But this will still be up on video on demand, so I'm going to continue working through my problems. And hopefully this will help you get an idea of what you're going to see, the types of problems you'll see on the test. Now, I do say this. Don't get angry when you see a problem that I didn't go over here on the test. Everything that we've done up to this point is fair game. I'm just giving you an idea of how I write the problems and how I use these problems in the assessment. All right. Yep, we're here. Sunny and rainy days. You are planning a 4-day trip to Seattle, Washington in October. Make a sunny day, rainy day tree diagram for your trip. I think we did this one in class. I did it off the top. I didn't have it so nicely copied and pasted. I just kind of did it over top, sunny and rainy. But here we go. I think it was when we had some rainy days in a row, some stormy days. So make a sunny day, rainy day tree diagram for your trip. Okay, no problem. I'm going to go, first day is going to be sunny or rainy. It can only be these two things given this particular, the way it's written. Okay. On the second day, and I'll just write that at the bottom because I don't know if I've got room at the top. If you have a sunny day the first day, no problem. The second day is also going to be sunny or rainy. If you have a rainy day on the first day, the second day is going to be sunny or rainy. And then on the third day, if you're sunny and sunny, on this third day, you could also be sunny or rainy. Same here. Same here. Whoops, my handwriting's need to focus. It's a me thing. Here we go. So there's my tree diagram. So make a sunny day, rainy day tree diagram for your trip. There it is. Now, it doesn't tell us what the probabilities are, but it's not asking for that here. But if it was, we could figure it out. But now it's asking for the sample space. So I'm going to go right over here in yellow. And I'm going to write the sample space knowing that I'm going to run out of room here. So I have to just put it below. So I've got the sample space is equal to, we'll start here, sunny, sunny, sunny. And then I'm going to have sunny, sunny, rainy. Then I'm going to have sunny, sunny. No, I'm done there. Sorry. Sunny, rainy, sunny. Then I'm going to have sunny, rainy, rainy. See if I can squeeze it in. Sunny, rainy, rainy. Got it. Now below it, I'm going to put the lower half of this tree diagram. So I'll start with yellow. I got rainy, sunny, sunny. So I've got rainy, sunny, sunny. I've got rainy, sunny, rainy. I've got rainy, rainy, sunny. And I've got rainy, rainy, rainy. There's the sample space, and the last question says, list the outcomes of the event it rains on exactly one day. Okay, so I have to think about this for a second, but before I move on, I built the tree diagram. Not a very hard tree diagram, and I was actually able to fit it in here, although it does still look a little funky because of my handwriting, but not too bad. Then I wrote the sample space over there to the side. I had to kind of stack on top because I ran out of room, and I have 8 possible outcomes. So I listed the sample space. Now it wants me to list the outcomes of the event it rains on exactly one day. Okay? Well, it rained exactly one day here. It rained exactly one day here. Exactly one, yeah. It rained exactly one day here. And that's it. So we've got sunny, sunny, rainy. Sunny, rainy, sunny. And rainy, sunny, sunny. That's the answer to C. Okay. This was the answer to B. Lowercase, but still. And A. Okay. So there we are. No questions. I'm not sure anybody's in here on the live right now. I think I'm going to try pushing back out to Twitch again just to get a few more folks through the Twitch app as well that at least are popping in. I stopped doing that because it took up a little bit too much bandwidth, and I thought I could save a little bit of, make the stream better for the YouTube if I did that, and it does seem to be better. So what I might do in case anybody listening is streaming themselves and may use Restream or Ecamm or things that I'm using, I may do what I did a while back, and I can push through Restream and make Restream push to 2 different or 3 different venues, and then it's not eating my system up. I'm only pushing out to one thing here. But it's all math. Okay. Let's look at conditional probability. A couple of problems here. Multiplication rule, then we'll look at a few with addition rule. All right. So conditional probability, these are some of the things that we talked about again in class in detail. Probability of an event occurring given that another event has already occurred. If the 2 events are independent, then that doesn't affect each other. If one is dependent on the other, then that affects the probability or the outcome of the probability itself. So let's look at the problem. Computers and internet access. A study found that 81% of households in the United States have computers. Of those 81%, 92% have internet access. Find the probability that a U.S. household selected at random has a computer and has internet access. So remember, in class we talked about you don't want this to be the only way you determine what kind of situation this is, but it's a good giveaway that we're going to use the multiplication rule, that we're looking the probability that a U.S. household selected at random has a computer and has internet access. Since we've got that and in there, then we're going to be using the multiplication rule. Which, yeah, I had it up here. Yeah. So when I was here a second ago, I did not go back to this, but this is what we're going to be using right here. So basically, this. So I'll just write it out. So I've got the probability of A and B is equal to the probability of A times the probability of B, right? So the probability of A is going to be has a computer. So 81% of households have computers. So you've got 0.81 here times the probability of B, which is have internet access, which is 92%, 0.92. Well, I don't know what that is. 0.81 times 0.92. There it is. It would help. This is what I came up with 74. Now right away, just like I talk about in class, I troubleshot that real quick. That doesn't fall in our range of probabilities rule. So now I look back and I didn't type hard enough on the calculator for the decimal, so I had 81 instead of 0.81. So let me try it again. Yeah, same number, just decimal. 0.7452. So you got about a 75% chance if you randomly select a household in this particular area or this particular population, you have a 75% chance that you will have both a computer and internet access. All right, not a bad problem. Moving on. Surviving surgery. A doctor gives a patient a 60% chance of surviving bypass surgery after a heart attack. If the patient survives the surgery, he has a 50% chance that the heart damage will heal. Find the probability that the patient survives surgery and the heart damage heals. I'm going to draw a tree diagram here, and I'm already recognizing that I don't even need to draw the whole thing. I only need one specific branch of it, a couple of branches of it. So if you've had a heart attack and you're having bypass surgery afterwards, and you're this patient, actually there's a little bit more to it. If you're this particular patient, the doctor gives a 60% chance of surviving. So there's either surviving or not surviving. And this is going to be 0.6. And down here this will be 0.4. All right. If the patient survives the surgery, he has a 50% chance that the heart damage will heal. Find the probability that the patient survives and the heart damage heals. We only care about the survive here. So if he survives, it's either going to heal or not heal. There's a 50% chance that it'll heal, which means there's a 50% chance that it won't heal. That's all we need in the tree diagram. And so now what we're going to do is just apply the multiplication rule. And a little bit different here. I don't need to necessarily write out. I don't need to necessarily write this out. But this is what I'm doing. So these are consecutive events. So you had a heart attack, which doesn't factor in here other than to set up the stage for this set here. After having a heart attack, the particular patient has a 60% chance of survival. And then if they survive, they have a 50% chance that they will heal, that the heart damage will heal. Okay. So all I'm going to do is take this times this. So 0.6 times 0.5 equals, isn't 6 times 5, 30? I'm going to say 0.30. Oh, it's great. Easy. Yeah, that's it. So you got a 30% chance of surviving the surgery and healing, the heart healing afterwards. Given the scenario, given the numbers by the doctor, given the numbers that the doctor prescribed. I'm losing my words. It's been a long day it's been a long day at work today. But there we go. And we've got the answer. So not too bad on this one either, I don't think. Now let's talk about the addition rule. I've got a couple of problems here, and then I'll close it out. I typically stay on here about 45 minutes. I have been on here tonight 38 minutes, so I'm right on time. And then I'll have one question at the end for you just with the calculators. Again, I want to show those screens. I'm really curious if folks come on here and can leave a comment afterwards, you can leave one there. But if you are in my class, just let me know which of the calculators you prefer. Don't need them tonight. I'm just kind of working on the side with my calculator. Okay, I put a summary of all the probabilities that we talked about tonight, or that I had in this presentation. I didn't necessarily go over all of them piece by piece. The summary of probability, those are the things that you're responsible for on the test. You already have these. You have the ability to do a 3x5 note card. for the test front and back, put everything you want on there. I have found over the years that if a student does that ahead of time and has that card ready, not 5 minutes before the test, but has it ahead of time and thinks through what they put on there, they typically know everything that's on there when they get to the test. But it just makes students feel more comfortable taking the test, so that's why I do it. Changes the outcome 0, in my opinion. The two events A and B are mutually exclusive if A and B cannot occur at the same time. One of the most heartily used examples in my classroom is when you're choosing just one card from a standard deck of cards. And let me put this disclaimer out there. If you are unsure about cards, you need to put the information on your 3x5 index card, or just learn more about regular deck of 52 cards. Choose one card from a standard deck. What is the probability that that card will be a queen or a 3? Well, those are mutually exclusive events, so it's 0. You can't get a queen and a 3 with the draw of one card, right? Or I'm sorry, I think I said or. If you're looking at the probability of that one card being a queen and a 3, it can occur. So those are mutually exclusive events. And that's going to come into play when we have to subtract out the overlap from the two events when they are dependent, or they have some overlap. You're taking into account that overlap in the first probability and the overlap in the second. So you have to subtract it off by taking out the probability of A and B occurring. Okay. Take a look at a problem. A single card is selected at random from a standard deck of 52 playing cards. Find each probability. And let me go ahead and write this out. Over here. Although I'll write up here in the white space, see if I've got room. So a standard deck of cards has 52 cards. 52 cards. It has 4 suits. It is spades, hearts, diamonds, and clubs. There are 13 each of these cards. Okay? So of spades, you've got 2 through 10, Jack, Queen, King, and Ace. With hearts, you've got the same. With clubs, you've got the same. With diamonds, you've got the same. That's it in a nutshell. Now, if you haven't played with them, I get it that it doesn't come to you readily. But practice a little bit with them for the test at least. Or have it written down in such a way, not like I just wrote it. I was trying to squeeze it in. Write it in such a way that when you refer back to it, it makes sense to you and you can pull the numbers out. All right. A card is selected at random from a standard deck. Find each probability. Find the probability of randomly selecting a club or a 3. So the probability of a club or a 3. Well, that's equal to the probability of a club plus the probability of a 3. Subtract the probability of a club and a 3. Now, can you choose a card that is a club and a 3? Yes, you can choose a 3 of clubs. Therefore, they are not mutually exclusive. This subtraction out, this overlap from, say, the Venn diagram, where they something they share, has a number. It's not a 0. So the probability of drawing a club, there are 13 clubs in the deck out of 52, plus probability of drawing a 3, there are 4 of those out of 52. Subtract out how many cards are a club and a 3. That's just 1. So I'm left with 13 plus 4, which is 17, minus 1 is 16, divided by 52. Remember, I asked you not to leave it as a fraction, although that's mathematically correct. I want it in more terms of what we're talking about in class. And we'll take it out here to 4 decimal places. 3077. So about a 31% chance of randomly selecting one card and it being a club or a 3. Okay, let's look at the second instance here. What's find each probability. So find the probability of randomly selecting a red suit or a king. So a red suit is diamonds and hearts. So we've got 26 cards there that are red. So we are looking at the probability of a red, I'll just put red card, plus the probability of a king, subtract out the probability of a red and a king. Again, there are 2 red kings in the deck, so I've got a number there. It doesn't just go to 0. They are not mutually exclusive. So the probability of drawing a red card is 26 out of 52. So you got a 50% chance of getting a red card. Plus the probability of a king. There are 4 kings in the deck. 4 out of 52. And then we subtract out the 2 red kings. So 2 out of 52. 26 plus 4 is 30 minus 2 is 28. 28 over 52. Again, that fraction is mathematically correct, but I want it as a decimal. So to be accurate, I'm working it out. 5385. So about a 54% chance of drawing 1 card randomly from a standard deck of cards and getting a red card or a king. Okay. The last one, randomly selecting a 9 or a face card. Right away, you should, if you know cards, you should recognize that those are mutually exclusive events. You can't draw a 9 and a face card. Face cards are Jack, Queen, and King of all 4 suits, right? And a 9 is a 9. 9 is not a Jack, Queen, or King. So if you were working this, randomly selecting a 9 or a face card, I'm sorry that I can't erase here. Let me go up to the upper corner, see if I've got room up here. So what I'm looking for is the probability of drawing a 9 or a face card. Okay? That's equal to the probability of drawing a 9 plus the probability of drawing a face card. I'm really squeezing it in up there. I don't subtract out anything because they're mutually exclusive events. You can't draw a 9 that is a face card or a face card that is a 9. So I'm left with just this. So the probability of drawing a 9 is 4 out of 52 plus, and the probability of drawing a face card, you got Jack, Queen, King, you got 3 times 4 is 12. So 12 over 52, there's no overlap. So you've got 16 over 52, which is accurately 3077. I did that already. It's right there below. So 3077. About 31%. All right. I know that's scribbled at the top. I apologize for that. But on Keynote, I'm still working on getting. I love that I can put my keynotes up here. It's very easy to write on and work on. But I run out of room, especially if I want to elaborate on something. Hence what I was working at the other day, where I was trying to have this up and something else up that I could work on. And I just dicked all my screens up, so I had to go back and kind of rework them. But I think I'm okay here. I don't think there's anybody here that's critiquing my screens and saying, my goodness, he'd be a much better streamer if he did. I don't think anybody's doing that. This is just a review for a test. All right. I don't want to do this one because I'm running out of steam here and I've got one on the back side. Let's take a look at this one, a little bit more context to it. So, a random sample of 250 working adults found that 37% accessed the internet at work, 44% accessed the internet at home, and 21% accessed the internet at both work and home. What is the probability that a person in this sample, selected at random, accesses the internet at home or at work? So you got 250 working adults. You're going to reach into the tub where they're all sitting and randomly pull one of them out. I always think of the old wee me's where you reached in and their legs were kicking. Anyway, you pull them out. What's the probability that the one person you pulled out accesses the internet at home or at work? Let's write that out. So what's the probability that they access at home or at work? Okay. Well, it's the probability that they access at home plus the probability that they access at work. Subtract out the probability that they access at home and at work. Well, even though this problem may seem sometimes a little bit more menacing because there's a lot of numbers thrown at you, you have to kind of read through it, figure it out. Everything is laid out pretty easily for you. If you can do what I've done up here and lay out the form of what we're working with an OR problem here, working with probability, and lay it out in form, filling in is pretty easy. So the probability of accessing the internet at home was 0.44. Plus, the probability of accessing the internet at work was 0.37. Right? 0.44 access it at home, 0.37 access at work, yes. And then you subtract out how many access it at both work and home. Access the internet at home or at work. So internet at home and work is 21%. Okay, so I got 0.44, 44 cents plus 37 cents, very easy. Subtract out 21 cents. Yeah. 0.6. That's it. That's the answer. So there you go. This is review number 1 for the test. This is just talking about a few samples of the types of problems that can be on the test next Wednesday from the probability section. We worked through this one. I skipped the rolling a die problem. It was more of the same, like flipping a coin. I just am running out of steam. Oops. We worked through randomly selecting cards. Understand you have to know the cards. So if you're not a cards player, I know a few of you were cards players, a few of you weren't. So write on your 3x5 index card or learn cards this week if you haven't learned them already. $1 pack of cards. Most people have them in their kitchen drawer somewhere, or buy some at the dollar store. I'm not trying to get you to spend money, but it might be a good way to learn these cards, and certainly a good way to interact with family. Play some hearts or spades. Very fun games. We talked about some overview things before I went into the problems with the addition rule. We did the multiplication rule. We worked through a problem with a tree diagram. Several tree diagrams, actually. We worked with some context problems there. Talked about the overview. That was conditional probability, the multiplication rule. And then we talked about some, And we talked about another tree diagram that we had to build and a sample space, and then pull out of that sample space the outcomes of the particular events that were asked for. Okay? And then another example, blah, 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 for basic probability. A very poorly drawn, but very accurately drawn tree diagram. Just has a lot of parts that are a little bit too big for my screen here. And then when you go back here, we had some overview. There we go. That's the end of my Chapter 3 review. I think that I've set a record here tonight. I had one person come by. Just one. Tiante stopped by and said hello. I spoke back. And somewhere along the lines, we lost Tiante. But we all know that it's going to be on here video on demand. There's no points given for this. I appreciate anybody that stops by and says hello. I truly do. One more review coming next Tuesday. I will work with discrete probability distributions again. I will walk through, especially with some problems dealing with the binomial distribution, which is my all-time favorite, and then regular probability distribution. Remember the one thing that I told you on an assessment coming up where those two things are thrown in there together, the biggest task on you is to be able to read a contextual problem and determine whether it's just a regular probability distribution that's based on some frequency table that you have to pull numbers out of, or if it's a binomial that fits the constraints of a binomial distribution. So we'll talk about that though next Tuesday. I'll be on at 7 o'clock Tuesday night. I may stream some this weekend. I may put a couple of extra videos up there with some stuff as I test my stream and try to get my screens right. Otherwise, I appreciate those of you who come by for the lives, and I truly appreciate those who come by for the video on demands. Like the videos, leave a comment. I always like the comments that are left on the lives or on the videos that I put up here. And follow the channel. I'm trying to keep some stuff up here for not only my stats class, but other students along the way that might stumble upon this and say, hey, this helped me a little bit. So that's it. That's all I got. Have a good rest of your week. In North Carolina, where I'm at, for those of you in my class, stay cool. It's very warm out there, very muggy. Stay cool, and I will see you next Tuesday if I don't see you in the grocery store somewhere between now and then. All right. Thanks.